Good morning, everyone. Today we will look at digital to analog converters. We call them DACs or DSCs. The three things to look at:
Here is Royal Mail. Have your urgent letter. 皇家邮政.
So the first thing we'll look at, it will take us 5 minutes or 10 minutes max, is simple op-amp circuits. Many DSCs are based on the op-amp circuitry that we developed. So the op-amp, the comparator are important for DSCs. The op-amp is many of the DSCs are based on the op-amp circuit. So we look at the simple op-amp circuit. Then the second thing we'll look at is, I think the general name is binary weighted DUCs. This come in two flavors, resistor weighted and capacitor weighted. The resistor one also has two parts to it, A and B. The third part, which we'll do on Wednesday, is potentiometric DSC, potentiometric. If the lecture today goes quickly, we might be able to get started with the third one, but the plan for today is to cover those first two items. So the first one, before the first one, just as a reminder what a DSC is. A DSC takes a digital input, B1, B2 to Bn. If we put this into a DSC, and the DSC will have a certain reference voltage, then we'll have an analog output. And this analog output is related to the reference voltage through this binary number is essentially a fraction. And we convert that into decimal, so it becomes B1 over 2, B2 over 2 to the power 1, plus Bn over 2 to the power n. And this is our DSC. So essentially, we want a summing function or capability within DSC. So what DSC does, we generate each of these individual signals as voltages, and then we sum them up. Yeah, that's what a DSC is. And the simple op-amp circuits that help us do this, they are in three flavors. The first one is what's called a summing amplifier. So all this for EEE students, many MSc students who've done EEE. So you've done this already in your undergrad, but just as a reminder, so that when we use the circuit, we are all on the same page. In a summing amplifier, you have your op-amp. The positive terminal is grounded. We have a feedback resistor there. And this is your V out, R feedback. And to generate a summing amplifier, we can have a resistor R1 there, R2, there could be other resistors there, Rn, and if this is V1, V2, and that's Vn. So we know what's inside the op-amp. We spent almost 2 weeks or 2.5 weeks discussing the circuitry of the op-amp. If we connect it in this configuration, because this is a high gain unit, the potential difference between the two is close to 0. So the potential at this point is almost identical. It's almost ground, and we call this point a virtual ground. And because of that, if you have a voltage V1 connected to this resistor, the potential there is 0. So you'll have a current I1 flowing in that branch, where I1 is equal to V1 over R1. And the second branch, you'll have a current I2. The current is actually independent because the potential there is set by the op-amp. The high gain of the op-amp ensures that there cannot be a large difference between the two between the two input points. I2 will be V2 over R2, and IN will be Vn over Rn. So the current that flows into the negative input of the op-amp, we can call it I0. And of course, we'll see that I0 is equal to I1 plus I2 and plus IN. So here, we really have our summing function. And so this is 0. The potential here is V out. The input to the negative terminal, you know, this is a MOS transistor. It's a PMOS transistor to be specific. So if this is a low frequency current, the DC currents, none of the currents flows into that. So the whole of this current I0 flows via the feedback resistor to the output. So we can say that, so if this is V out, that's the potential difference between that point and that point. That is 0, that's V out. So the current is going kind of going in the negative direction. So we can write that V out is minus I0 times RF. If we put in this into that expression and put that into this, we'll see that V out is equal to minus RF into V1 over R1 plus V2 over R2 plus Vn over Rn. So if you compare this expression with this expression, you can see that they're nearly, if we make our choices of V and our choices of R and RF properly, we make good choices, the two expressions will be identical. So that's our first DSC with a good choice of, so for example, if we make V1 is equal to V2 is equal to Vn, and this is equal to Vref, or is equal to minus Vref, then we generate that. And if we make R2 to be equal to twice R1 and R3 to be equal to 4R1 and Rn to be equal to twice n minus 1 R1, then you'll see that this circuit generates, then this expression will be identical to that expression, and therefore this circuit is will work as a DSC. Yeah, but for it to work as a DSC, we need to introduce switches that enable us to, if B1 is a 0, we don't use this current in the total sum. If any of the bits is a 0, that current should not go should not count towards the output voltage. So I already draw. So this is a summing amplifier. Now we can draw what's called a weighted Yeah, so we can do what's called a weighted resistor DSC. It's a little bit off the plan. I needed to do the simple circuits first, but yeah, that's the simple circuits. But I think we can do the first DSC based on that simple circuit. So if this is VREF and this is R1 and this goes into a switch. If this is R, this one I can make this twice R. And this one goes into a switch. The switch is controlled by B1. This one is controlled by B2. And the last one here, I can make it twice N minus 1 times R. And the switch here is controlled by Bn. And all this goes into the inverting input of the op-amp. And this terminal is grounded. And this is V out. So RF in terms of R, how must we pick that to be? RF must be equal to half R? Yes or no? Someone confirm to me in the chat. And therefore V out, so the current here is I1, I2, and the current here is IN. The total current there is I out. The potential there is 0 volts or virtual ground. And V out is equal to the sum of the current is minus I naught times RF. Of course, here I1 is equal to B1. If B1 is 1, then the switch is closed. So the current I1 contributes to the output current. So we have VREF divided by R. I2 is B2 times VREF divided by twice R. I choose the values of the resistors so that I have the weighting for the various currents as and IN will be equal to BN VREF divided by twice N minus 1 times R. And therefore V out here. So I think I have to choose RF to be equal to half R. And if I do that, I'll have V out is equal to minus VREF B1 over 2 plus B2 over 2 squared plus Bn over 2 to power n. So we have our digital converter. Of course, we have a negative sign there, but we can always invert the signal, and we have our DSC. So with an op-amp in summing configuration, we can make a simple, it's quite easy. If we have a digital inputs, B1, B2 up to Bn, we just need to construct this circuit. We know how to do the op-amp. The MOS devices can also be used as switches, as you know. So we know how to do that. We can realize the resistors, and there we have our DSC. In actual circuits, N is limited to 8 bits or less, and we haven't had a tutorial yet. We'll discuss that. I think I'll schedule a tutorial session in before the end of this, probably one of the lectures next week. We can discuss why the actual number of bits is less than normally we implement this for up to an 8-bit DSC. Just as if the current here is I, the current here, you should be able to see that it's half the, so the current divides by half as you go down this resistor network. So we've already, what can I say? We've done one simple circuit. There are actually 3 simple circuits, 1, 2, 3. So the summing amplifier is the simplest op-amp circuit that we use. There are 2 others that we look at in a minute. The weighted resistor, it has 2 versions. We've already looked at the first one, which is based on the summing amplifier. So before we carry on to the second simple circuit, no, I think now we do the second and third simple circuits. Second basic op-amp circuit. So the first one was a summing amplifier. This one, we can call it a buffer, or also called a voltage follower. So this one is quite simple to. This one is so also based on op-amp, minus, plus. So in a voltage follower, well, I'll give you the circuit because you probably did this many years ago, and you may not remember. V out, V in. So the input voltage, we put it onto as input to the positive input, and we connect the negative input to the output. Remember, because of the high gain of the op-amp, whatever the potential is here will be this circuit. Whatever the potential is here, there cannot be a huge difference in voltage between those 2 inputs. So if this is V in, the voltage there will also be V in, and therefore V out is equal to V in. We call this a buffer or voltage follower. As you can see, this is the input voltage. V out is equal to V in. And yeah, so the name voltage follower is quite natural for this circuit. And it's also used in dark configurations, as we'll see shortly in 5 or 10 minutes. It's also called a buffer because the input Z in, is it low or high? Could someone type that in the chat? What's the input impedance into the, so the input impedance is high and the output impedance is low. And that's a characteristic of what's called a buffer. So the input signal is actually isolated from the output signal. You can make whatever happens on the input side is not affected, or whatever load you put on the output side doesn't change your circuit functionality on the input side. So this is, yeah, it's called a voltage follower. A circuit which we didn't do in class is NMOS or PMOS source follower. So you may have done this in your undergrad, but if you haven't done it, it's a useful circuit, you know. Yeah, because if you go for an interview and you know there's someone asks you what's a source follower. So source follower is also a voltage follower, but it doesn't. This voltage follower uses op-amp, but you could do a source follower using an NMOS device or PMOS device. Its other name is a common drain amplifier. So I'll leave that as homework, also as something that we may discuss during our revision class if you have issues with that. But please, yeah, as anyone who is doing a VLSI course, you need to know what a source follower is. So, but some of you already know this from your undergrad, or most of you should know that, and just beware. So that's the second op-amp circuit. This one, it's useful for the weighted capacitor DSC. So we'll look at it in 10 minutes at the weighted capacitor DSC. And this is circuit A in terms of a basic op-amp circuit that we'll use to realize a source follower. The sister to this circuit is the same circuit, but it has amplification, which is B. So if we have an op-amp, we can create a source, we can create a buffer or a voltage follower with amplification in it. And if this is V in, yeah, I think this is how we do the amplification. For V out, we choose two resistors. This is R1, and this one we grounded there, and here we put a feedback resistor R2, and our output looks like that. So this is a buffer or voltage follower with amplification. So it's not only the output voltage not only follows the input, but it gives amplification where K is greater than 1. The other voltage follower we did, it just follows the input voltage, so there's no amplification. K is equal to 1. So for this one, if we choose the resistors properly, K is greater than 1. Does someone know the expression for K or derive it? Should take a minute or two to derive it. So K, I think, is equal to 1 plus R2 over R1. Is that correct? I'll give you a minute or two to try and see if you can derive that. I'll give you a hint. So if this is V in, the potential there, you should know what it is. So if you know the potential at that point, this is V out, you know that the voltage there, you know the resistor values. Could someone confirm whether this is correct, whether K is equal to 1? So yeah, so this is correct. So that's one person. Another person to confirm whether that's correct. But you should be able to derive that easily. In the time I've been talking, you have V out, you know that's you know the voltage there. So one person says that's correct. Anyone else? One of the MSc students could. So two people say that, and both of you are BEng students. I'm waiting for an MSc student now to BEng or MEng. An MSc student to confirm that that is correct before we carry on. I'll do that as homework also. Yeah, thanks, John. Yeah, so 3 people. I think that's correct. And if you please derive that. When you do that, you don't need to memorize these things. It's much easier if you need to use the circuit. You just do it because you know it. So just as a reminder of where we are, the summing. So the first circuit of the simple circuits, the summing amplifier, and we've already used it to do the first weighted binary weighted DAC, the weighted resistor DAC. The second one is voltage follower with the no amplification. So the output voltage just follows the input voltage, but it offers the buffer function because the input voltage sees a high impedance while the output voltage sees a low impedance, and you isolate the output from the input. And the third one is the buffer with amplification. The second and third, they're used in DAC circuits, and as we'll see shortly. So the next thing we do is a variation of the weighted resistor weighted DSC. Resistor weighted DSC. And this one is actually this resistor weighted DSC, we'll just do it and then we can compare and contrast it with the first one. It actually develops directly from what we've looked at this as the summing amplifier, but yeah, it's based on a very simple concept, which is written in the name. So if I start off with a resistor whose value is twice R, and then in parallel, I put another resistor whose value is R. These two resistances are in parallel, and therefore, if I look at the circuit to the right, the input resistance that I see there is R. So if I just looked from that point to the right, the input resistance there I see is 2R. By introducing another resistor of equal value, which is grounded, the input resistance from the left-hand side of this branch, just looking to the whole circuit to the right, is R. And if I introduce another resistor there, I could make this to be 2R so that it looks like it's that. If you think about it, the resistor value that I need to introduce there is R. So if I introduce a resistor R there, the input resistance I look towards the right is identical to the resistance I see from here towards the right is R. And because the resistance to the right there is R, I can create another branch here to ground, and its value is 2R. And therefore, at this point, if I look to the right, the resistance is R. And so this circuit goes on like that. I'll use 3 of them. That should be enough. So for this one, if I have a reference current flowing in there, IREF, then the current I1 would be IREF divided by 2. Because the resistance we see at this point towards the right is 2R. The resistance to ground here is 2R. So IREF divides equal between those two branches. I2, you should be able to see that I2, in terms of IREF, the reference current, it will divide it by 4. So because only half of IREF reference current comes this way, when it reaches here, at this node, the resistance towards this path and this path are identical, both 2R. So only half the current comes there, and therefore I should actually just write it as IREF over 4, which is IREF over 2 squared, and so that's I2 and I3. I3, you should be able to see that this is IREF over 8, or IREF reference current over 2 cubed. And if we remind ourselves, V out for DAC, what we're looking for is a circuit that generates this expression B1 over 2, B2 over 2 squared, B3 over 2 cubed, up to Bn over 2 to power n. So you can see that the currents through these branches give us the weighting that we need. And so if these currents, instead of taking them to ground, we take them to the summing amplifier. So the summing amplifier can sum these currents. And then we need to introduce switches here, such that if the introduction of the switches has to be slightly smarter than in the first DSC. So if we sum those currents, we'll have a 3-bit DSC with this circuit. And IREF in terms of VREF, I think the total resistance there is R. IREF, I think, will be given by that for the circuit which I have there. if Vref is there, the total resistance we see is R, and so the reference current will be that, and half of it will come through this branch. The second half, a quarter of it will go through this branch, and eighth of the reference current will go through the third branch. So with that, we are ready to draw the schematic. So this uses, so we need the summing amplifier because we need to sum I1, I2, I3. If all the bits are 1, we need to sum all these currents, and so we can use the summing amplifier configuration to do that. And we want the resistors to be large or small. We want the resistors, if they're too small, you have a lot of, so this is an engineering judgment you have to make, Mohammed. If the resistors are too small, you have a lot of, the current is quite high, and so you have the I squared R loss becomes an issue. So the chip will heat up quickly because I squared times R, this becomes like your old bulbs, so it becomes like a little heater. If the resistance is very high, the size of so sizing of the size of, so we want a good size, and we want the current not to be too high. So it would be in the kilo ohm or hundreds of kilo ohm range. So too low, it will consume too high currents. Too high, the accuracy, we'd like that these resistors are matched. So when you make a chip, it's easier to make. So there's an engineering judgment we have to make in terms of the size of the resistor, but tens of kilo ohms to, not too high. So let's do our weighted resistor DAC based on this circuit. So this circuit is called R to R circuit. R to R weighted resistor DSC. That's what it's called because we have a ladder that comprises resistance 2R and resistance R and 2R. So we'll do it for just from this circuit. So I'll draw the summing amplifier. And for the summing amplifier, that's ground. And here, I'll have my terminating resistance, whose value is twice R. And the first resistance here, which takes an eighth of the current if we're doing 3-bit, that's also twice R. And at this point, we come into a switch. And this switch is controlled by bit B3, because the one closest to the DAC will be the lowest weighting. And if B3 is 1, the switch is closed and the current comes here. And here we'll have our reference, our feedback resistor, RF, that's V out. So if the switch is connected there, the current I3 will flow into the negative terminal of the op-amp, but of course all of it comes like that to the output, and it will contribute to it will compute to V out. However, if B3 is 0, this current should not come this way because that bit B3 is not contributing to the output. But we still need I3 to be here, otherwise this circuit doesn't work because all the currents must be flowing all the time. And therefore this, at this point, I would connect that to that, and I would connect that to the ground of the circuit. So this switch, it's either connected to this ground or it's connected to the virtual ground, so that I3 flows all the time. If B3 is 1, I3 flows, contributes to the output voltage. But if B3 is 0, it doesn't contribute to the output voltage. We redirect it to go to ground. And then the next resistor value there, we know has to be R. And for B2, it also flows through 2R, and here we need another switch. So I can draw that like that. And this is controlled by B2. So the operation of that is identical to B3. B2 is equal to 1, the current contributes to V out. If B2 is equal to 0, it doesn't contribute to V out, it's directed to ground. That's I2. And this would be R, twice R. And I've drawn that wrongly. We need R at that point. And this goes to ground, and this is controlled by B1. And this is my RF. At that point, we can call it VREF. So there you have it. This is your 3-bit. This is your 3-bit R to R weighted resistor DSC. Compared to the earlier DSC that we looked at, the current flow there is I1. So I1 gets only half the reference current that flows into the whole of this circuit, and it either contributes to V out if B1 is 1, or it doesn't and is routed to ground, and the rest of the switches work that way. So here we only have two resistor values, 2R and R, and therefore we can make them accurately. Having said that, even here, the largest value of DAC we make using this architecture is less than 8. If we compare this circuit to the earlier weighted resistor DSC, here the range of the resistors is pretty large. So if this is R, for 3-bit, this will be 4 times bigger. Yeah, it will be 4 times bigger. If it's 8-bit, the range of the smallest resistor to the largest resistor is quite large. And from your lab, you should have an appreciation of when you lay out these devices, the chip area that they take. For the different sizes, they'll take different size chip areas. And that means the accuracy of making the smaller resistor and the larger resistor, the accuracy will not be the same. And that's why this is a better implementation, because you only have 2 resistor values that you need to deal with. But nonetheless, the reference current divides by 2. And if you have up to 8 bits, the current I1 to current in the 8th branch, the ratio between the currents is quite high. So if this is a milliamp, then the current in the 8th branch is almost in the noise level. And yeah, so one needs to make engineering judgments there. So just to recap where we are, we've looked at those 3. We've looked at the 2 types of weighted resistor. I call them resistor weighted. It should be actually weighted resistor. Weighted resistor DAC, and that should be weighted capacitor DSC. And we've looked at the 2 weighted resistor DSCs. Here, the range of resistor values here is quite large. Here we only have 2 resistor values. Here we need a simple switch. Here the switch needs to switch between virtual ground and actual ground. Yeah, but they do the same things. Just so with your op-amp in the summing configuration, you can do your weighted resistor DSC. But from the question from Mohammed, we know that the weighted resistor DSCs, they consume your power, your battery. So batteries always comes at a premium. And an alternative, which is the more popular implementations, to use capacitors, because capacitors do not tend to, they don't consume power. They'll store energy and release it back, but they'll not dissipate it. The resistors, they dissipate the energy that you supply to them. So next we look at the weighted capacitor DSC. We'll start with it. We just have enough time to get started with the weighted capacitor DSC. So weighted capacitor DSC. It uses capacitor array for summing and an op-amp as a buffer. And I think it's useful to state that right up front. We'll use the op-amp as the buffer, and we'll use the capacitor as our summing circuit. And how to do this? I'll do this for, I'll do this. We'll start, this is best done by example. So we'll do this by example, and I'll start with the 1-bit DAC using capacitors. So we'll not go directly to it, but we'll look at it. If I have a capacitor circuit, and that's my reference voltage, the capacitor circuit that we use is a capacitor as a potential divider. If this is capacitance C1, I let this one also be C1. V out here, V out, if I call this C2, I should call this C2. V out, you should know that V out is equal to that times V ref. As part of homework, if you don't remember that, please do that as your homework. Show that V out. If you consider this as impedances, V out is equal to not C2, this must be C1. If this is Z2 and this is Z1, what you know is that V out is equal to Z2 over Z1 plus Z2 Vref. All of us should know that. And if you put in the expressions for capacitors, this expression simplifies into that expression. That the output voltage here, if I have a capacitor as a potential divider, is the capacitance connected to Vref divided by the sum of the capacitances. That gives us Vref. So of course, if we choose this will be equal to half Vref. If we choose C1 is equal to C2. If we choose C1 to be equal to C2, we have half Vref. And of course, if we only have a 1-bit DSC, which we do on this course, eventually when we do sigma to delta DSCs, we'll see that a 1-bit DSC already does the job for us. The other way is to generate the other bits. So we have the 1/2 of this value 2. So the first bit B1, it's always scaled by half and Vref over 2. So this circuit, if we connect it properly, it can do for us V out will be equal to half Vref, which is a 1-bit DSC. So we need to introduce the B1 to control. We need to introduce B1 to control whether B1 is 0. Of course, if B1 is 0, output should be 0. And if B1 is 1, output should be equal to half Vref. So we need to introduce B1 to that. And then we'll get V out that gives us the right value. And you'll see that we need a buffer at this output so that the voltage that is here is not compromised by the output circuit. So we need to isolate a voltage that appears here from the rest of the circuitry, and that's why we need the buffer. So we'll redraw this circuit, introducing the switch that controls B1. So if we do that, that will be us for today. So first of all, I'll start by drawing the buffer. So V out will come into the buffer, and the reason for that should be clear to you. We only have capacitor circuits on our left-hand side. This point is our V out. So we have capacitor circuits on the left-hand side, and whatever voltage we have here, we need it to appear there. And whatever I connect here, if we have a resistive load here, it should not change this potential. So that's why we need the buffer there. And on this side, just give me a second. I need to draw this properly. I just refer to my notes for a second. So so if this is my V out, capacitor C2, I can draw it there and connect it to ground. And capacitor C1 from the previous circuit, remember this is our previous circuit, and I've drawn V out, included a buffer so that this output, whatever voltage we have here is isolated from our actual output. I've drawn C2, so I need to draw C1 and introduce the switch B1. So if this is C2, so C1 would come here. C1. Oh, just 1 second. I have a memory. Just give me a second. I need to organize my thoughts. Let's do this in person on Wednesday. I need like 5 minutes to do this properly. I'm trying to finish it quickly. Let's have an early break. We started on the hour, so we pick up from here next Wednesday. So we do the one bit. You can try to do it before the Wednesday lecture. Let's stop there. So we start Wednesday there, so we do it properly. Okay, so let's take care and see you on Wednesday. You can try to do that as your homework, to do the one bit weighted capacitor DSC. Okay, cheerio. See you Wednesday.